Welcome to the Fall 2018 Paul G. Allen Center for Computer Science and Engineering Colloquium. So we're rebooting the Colloquium to a model that we used to have in the department, where on non-distinguished lecture weeks, we hear about work going on, here at home. And hopefully this will help, as we grow as a department, keep that sort of small, close, close-knit family kind of feeling. So today, to kick things off, I wanted to sort of introduce folks who are new or remind folks who've been here for a while about the programming languages and software engineering group. And as a research field, we study a lot of topics that y'all are familiar with. These are the sorts of things that, as an engineer in computer science, day to day you deal with and try to tackle. And why do we study these things, right? Like, what's so interesting about these mechanics? Well, I don't know about you, but for me, programming is still often a huge challenge. And this is a bummer because it turns out that programming software is this sort of miraculous artifact that everybody uses to solve all of the hardest problems. So if programming is hard, but software is essential to solving the world's toughest problems, this is sort of a worthy cause, something worth investigating. And so our goal is to move from this world where programming is a tedious and error-prone task to one where it's more effective, more enjoyable, and more fun. And we do have a lot of fun doing it. So the Pulse group has a great culture, a lot of goofy stuff going on. And we'd love to hang out with folks. So you're always welcome to come swing by the lab and see what's going on. So the format today is we're going to have the graduating students from the Pulse group each give you sort of a quick elevator-ish pitch of their thesis results and what they've been up to for the past several years. So, you can all read and you're going to hear from these folks. One thing I did want to mention, though, unfortunately, Sarah's traveling and wasn't able to make it to the session today, but you should absolutely check out her work on end-user programming with the Helena tool that enables sort of non-programmers, non-experts to do really sophisticated web scraping automatically. It's super slick stuff. So without further ado, we will kick it off with James Bornholt, who's going to tell us about some amazing synthesis results.
Thanks. So yeah, my name is James Bornholt, and I want to tell you about some really exciting advances in the way that we build software that we can rely on. So I want to start by telling you about an application that we all rely on, that we all trust explicitly, which is Snapchat. Now, I don't really understand Snapchat, but I understand there's something with like photos or something like that. And so it probably has this function called take photo, right? Now, take photo takes as input the size of the photo we want to take, and it does some stuff with photos, and then it returns you a photo. Now, I don't know how hard this function is to write, but it's probably pretty hard. So what do we do to build functions that are hard to write? Well, you probably know the answer, right? The answer is we test these functions. So if we don't know how good take photo is, maybe we'll test it with some inputs. Maybe we'll see what happens when we give it 0 as a size, see what happens when we give it 1 as a size, and 10 and 100. And once we have a version of take photo that works for these test cases, we're totally happy. We're going to ship our app, and people are going to be happy with it. And let's say that maybe later on we discover that actually we made a mistake. We should have tested the case where size was 7. Now for Snapchat, this isn't a big deal, right? They just add their this test case to the suite, they fix the bug, they ship a new version of Snapchat, and everybody's happy. This works fine for apps like Snapchat. There's some applications where this doesn't work so well. The autopilot that flies my airplane, I don't want it tested on 4 test cases, right? I want it to be correct for every single input to this function. I don't want people to be discovering later on, oh yeah, by the way, when altitude is 7, something bad happens. So we need to do better for this kind of software. What can we do for software that's really critical to systems, to life? How do we build better software for those applications? So the programming languages community actually has a solution for this, and has had it for a long time. And it's 2 things. The first one is verification. Now, verification is something you're going to hear a lot about in the next few talks. But basically, you can think of verification as a form of exhaustive testing, right? So verification actually is a way of constructing evidence or a proof that a function works for every input we give it, right? No matter what input we give to our program, we get the right output. Synthesis is kind of an extension of that. So if you know what the function is supposed to do, if you actually have a specification of what you want a function to do, then using synthesis, we can actually just generate the program automatically. So save you from the effort of writing the program, just generate it automatically from the thing that you wanted. And these are 2 really powerful techniques in programming languages. So what I want to show you today is 2 things. The first thing I want to show you is an example of a verification and a synthesis tool. And for me, it's going to be an example that comes from the file systems domain. But the reason I'm showing you this example is not because I think file systems are especially compelling for everybody, but rather because I want to show you a second thing, which is that it's getting easier and easier to build verification and synthesis tools for X, for the domains that you care about, for programming languages problems that you have in your work. So those are the 2 things I want to show you. So let's start talking a little bit about file systems. So file systems are this really interesting domain that probably everyone is familiar with, right? So here's a really common example of something you've probably written code for before, and that most applications have to do. Let's imagine that you have a file in your file system, and it's called foo. And what you want to do is you want to update the contents of that file to be the string hello. Now, there's a variety of ways to do this, but this is a pretty common task. You know, something like SQLite has to do this when you write to your database. Microsoft Word has to do this when you write to your documents. A very common programming task. And I want to show you one solution to this programming task. So here's the program. You can ignore the first line here, but I want to point out the second line and so on. So what we're going to do here is we're first going to actually open a temporary file, right? A file called foo.temp. We're going to write our string into the temporary file, close the temporary file, and then finally we're going to rename the temporary file over the top of the original one. So this is a way of accomplishing our goal, right? Because at the end of this program, what will have happened is we'll have a file called foo, and it will have the contents hello that we wanted it to have. At least that's the intention, right? Now we built a tool that we call Ferrite. And Ferrite is a tool for verifying programs like this one, for checking that actually this program does what I just told you it does. And so the way that Ferrite works is that we write an assertion at the end of this program. And the assertion is just saying what I just told you, that after the program runs, when we read from the file foo, we should get the string hello, right? So I can run Ferrite on this program for you right now. And it's very quickly going to tell you that this program is wrong. So what's going on here is that Ferrite is actually pointing out a really subtle thing, which is that this program is correct when it runs to completion, but it's wrong if the program crashes halfway through. And in particular, what the output is saying is that if this program crashes halfway through, you can end up in a situation where your file foo is empty, right? Its contents is the empty string, which clearly isn't what we wanted, right? Now, Ferrite is also capable of taking this program and fixing it automatically for you. I don't have time to show you that, so I'm just going to fix it for you manually. The missing thing here is a little bit of synchronization, right? So we're going to add some synchronization saying that we have to flush the contents of the file before we do the renaming. If we run Ferrite on this version of the program, it's going to come back and say that it's happy, right? So this is a kind of powerful tool that we can write for any particular domain that you're interested in. Now, why am I showing you this, right? File systems are really cool. This is a really important problem. But the reason I'm showing you this demo is not because file systems are something that you need to work on, but because this tool is something that you might want to build for your domain. So let me tell you about how it's getting easier to build tools like Ferrite for your domain now. So what's hard about building a tool like Ferrite? Well, let me give you an example. Here's a really simple program. It's very silly. What this program does is it takes two inputs, two numbers, and it gives you back the largest one of those numbers that's even, right? So if you give it 5 and 6, you get back 6. If you give it 6 and 7, you get back 6. And it does it in kind of a silly way, right? What it does is it builds a list, x0, x1. It filters that list down to have only the even elements, and then it returns you the maximum of that list. Now, when you give this function concrete inputs, it's kind of obvious what it does. But in tools like Ferrite, and in verification tools and synthesis tools more generally, we don't give functions like this concrete inputs. We're actually giving them unknown inputs, unknown numbers. So for verification tools, we're giving it unknown numbers because we're searching for an input that breaks this program. So we don't know what that input is. For synthesis tools, we don't know what the program is, right? We're trying to find a program that works for any value of x0 and x1. So again, we don't know the values of these inputs. Now the problem is that when we don't know the values of these inputs, the way this program runs is really weird, right? So for example, when we go to do this filter predicate here, right, we're trying to take this list x0, x1, and filter it down only to the elements that are even. But we don't know if the elements are even, right? We don't know if x0 and x1 are even. So what we have to do is fork, right? We have to create two paths through this program. One where we assumed x0 was even, one where we assumed that x0 was not even. And then do the same thing for x1, right? So now rather than just having one return value from this filter function, we actually have 4 return values, the 4 possibilities, depending on the assumptions we made about the inputs. And then only once we've done this can we actually think about running the second line of this program, right, the max. Except we can't just run it once anymore, because there are 4 paths now. So we have to run this once for every path we created. So this is the thing that makes building tools like Ferrite really hard, right? It has this kind of unusual execution model you probably haven't seen before. And you can also probably see that this is kind of an exponential blow-up, right? The number of branches in this thing is exponential in the number of branches in your program. So programming at this kind of model is really difficult. So we've been working on a lot of things to try to make this kind of programming model easier for people to use. I want to show you just one example. It's a tool we built called a symbolic profiler. Now, a symbolic profiler is a lot like a regular profiler. It's designed to identify bottlenecks in your code, parts where your code is not scaling well or not performing well. But the difference with a symbolic profiler is that it understands that really weird all-path execution model of tools like Ferrite, of verification tools and synthesis tools. Now, I don't have time to go into the details about how it works, so I just want to show you firstly that it's really fun to watch. And secondly, and more importantly, we actually got some really interesting results using our symbolic profiler. So we took a variety of real-world automated reasoning tools. These are verification tools, synthesis tools that people are actually using in the real world. And we were able to make them anywhere from 6 times faster to 300 times faster. So for example, there's a really cool verification tool being used down at the UW Medical Center. It was actually built by folks here in the Allen School. And what it does is it verifies the software of a radiotherapy system they have there. And we were able to make that tool 300 times faster. That's really exciting for the people who use that tool, right? That tool is now basically instantaneous. So their development model is much better. So this is an example of the kinds of tools we've been building to make it easier to build your own verification and synthesis tools. So really, like, the bottom line here is that I think it's getting a lot easier to build these kinds of tools. Right? It used to be back in the good old days that building a tool like Ferrite or verification tool or synthesis tool for the domains that you're interested in took multiple PhDs worth of effort. Right? This was a really difficult task. That's gotten a lot easier recently, to the point where basically you can do what I did and get a PhD in formal methods. Well, I hope I did anyway. And you only need one PhD to do this now. Right? I built Ferrite. I built a couple of tools like that. But actually, we're getting to a more mature stage now, right? Like, we have things like profilers. We have debugging tools. We have abstractions for building these kinds of verification and synthesis tools, to the point where I think now it's actually possible for you to build one without having a PhD in formal methods. So take this domain X that you're interested in, that you have expertise in, and build a tool like this. I'm always really happy to talk to folks who are interested in working on things like this, who have domains that they're really interested in finding solutions to. And thanks very much for your time.
All right, so today I'm going to tell you about why static analysis is awful, but before I do that, I want to first tell you why static analysis is actually awesome. So what static analysis lets us do is take some program that we're interested in. Here, this is a simple program, but it could be anything. We're just iterating over an array of numbers and writing them to the output. And then a set of properties that we might be interested in. For example, we want to make sure that all of our array axes are within bounds, or that there are no memory leaks, or that we never dereference null. And static analysis lets us build an analysis that if it ever comes back true for a given property in a program, then if we ever run that program, that property is guaranteed to hold. So for example, we might have the property no leaks, and if our analysis says that there are going to be no memory leaks in the program, then when we run the program, there was, by gosh, will be no memory leaks. And we can do this also for null pointer exceptions. And what static analysis lets us do is that, although I've been talking about these specific properties in these specific program, it lets us talk about some arbitrary program and some arbitrary property, and lets us build these analyses in a principled way such that this implication holds. And this can hold even when that lets us get these computable properties, or analyses rather, even when the property in question, it might be undecidable. So the foundational result in static analysis is abstract interpretation, which goes back to the 1970s. An abstract interpretation uses this beautiful theory of lattices and monotone functions, and has given us a huge array of properties that can be verified using static analysis. And further advances have allowed abstract interpretation to be applied to programs that support features like loops and arrays and linear arithmetic. So, what's the problem? This sounds great. We have a way for programmers to automatically get guarantees about their program's behavior, even when those properties might in general be undecidable. So the problem is that programs today do not just write simple array manipulation programs. They are often using what we call frameworks, which are these scaffoldings onto which they can build the applications that they're trying to build. And these things handle the boilerplate and boring parts of application construction. And this is just a small sampling of Java frameworks that I found while searching GitHub for maybe 10 minutes. Because these frameworks are the common building block for a lot of different types of applications, this also means that they have to be as flexible as possible. And this means that they have an enormous amount of complexity. So this means a lot of reflection use, enormous libraries, a lot of layers of abstraction. And to give you an idea about what this complexity looks like, I want to show you my personal white whale when it comes to this, Spring, which is a Java web application framework. And this is a stack trace that I encountered while analyzing a Java application. And now this looks really bad, but it's actually worse because I lied to you. This is not the stack trace. This is actually the stack trace. And if you look closely, which you can't because the font is just too small, you'll see things like a cached introspection results, an abstract AutoWire capable bean factory, and a default singleton bean registry. So this looks very complex. These are all ridiculous names, so they must be doing something very complex. So maybe this is an unfair comparison. This is some complex, distributed application. So what this stack trace is actually doing is it instantiating this class. There are more bits of information in the stack trace than in the class definition itself. So the point I'm trying to make here is that even the most trivial applications, when they use frameworks, will encounter the full complexity of frameworks. And even the most simple framework-based applications will eventually reach this stack trace. And this is going to be very bad news for anyone trying to do naive abstract interpretation on framework implementations and the applications built on top of them. So we have this gap here between this wonderful mathematical theory that tells us how to reason about these programs' behavior without having to run them in a finite amount of time. And then on the other hand, we have the actual practice as performed by the software engineers today. So how can we bridge this gap? So obviously, static analysis is actually used today on real software. So what are people doing? Well, they might be writing, this is the state of the art, they might be writing models. And these are executable specifications of the framework's behavior. So the way you write one of these models is that you read the Spring reference documentation, which is a 1,000-page tome, and then you write models that describe how the framework behaves, so you don't have to actually directly analyze the implementation. It may not surprise you to learn that, given how long this reference documentation is, that these models go on and on and on. And again, I want to stress that this is the state of the art for analyzing framework-based applications this year in 2018. And this is just untenable, especially given the number of frameworks out there, the numbers that are popping up every single day. And so I claim that, at least in the context of context flow and heap-sensitive whole program analysis, we must do better, especially if we want to bring this wonderful promise of static analysis to programmers today. We can't say, we have this excellent tool you can use to verify your programs, but first read this 1,000-page document, write pages and pages and pages and pages of models, and then you can prove that your Tinder for dogs doesn't access out-of-bounds array indices. So I will say that I think we can do better, and that's what my research has been focused on. In particular, I've been working on a project called Concerto, which is a hybrid analysis framework that enables the precise analysis of frameworks-based applications without any manual modeling. The high-level idea is as follows. We start by analyzing application code using our old friend abstract interpretation. But the minute the application calls into the framework, the abstract interpreter yields into a concrete interpreter. And when I say concrete interpreter, I do mean we just run the framework code. And then when the framework code calls back into the application, we yield back into the abstract interpreter. And this process can repeat through nested calls and returns. So obviously, running the framework is a very precise way to reason about its behavior. But how can we possibly do this and still retain that key computability property? Well, there are two key observations that we've made about framework behavior. The first is that framework behavior is almost entirely determined by the contents of static configuration files. So if we have these configuration files and we plug them into the framework, they just take a single path of execution and then stop. They do what they're going to do and then stop. And further, it often happens that these files are available to us at analysis time. So when we run these frameworks, they can just open up these configuration files, parse their AutoWire abstract bean factories or what have you, compute what they're going to compute, and then return a single result back to the abstract interpreter. This is obviously quite tricky in practice, and there are a lot of technical details that I simply don't have time to go into. But for example, how do we exchange the values between these interpreters? In one hand, we have these abstract values that are summaries of possibly infinite sets of concrete values, and on the other hand, we have a concrete interpreter that expects honest-to-God integers. So how can we actually exchange these values in a way that everything sort of works and so that we don't have to have a tight coupling between these two components? I said that framework behavior is mostly determined by configuration files, but that might not necessarily be the case. The framework may read from the network. They might access non-deterministic user input. So how can we handle that in a way that still lets us retain this computability? Can we have the framework, the concrete interpreter and the abstract interpreter cooperate in some way and share information about their shared values? And there's a lot more. And I hope that you'll trust me that we have actually found sound solution to these problems that lets us retain the soundness of the overall analysis. So in summary, Concerto is a principled combination of concrete and abstract interpretation that precisely analyzes these framework-based applications. And we actually could reuse the foundational results from 40 years of abstract interpretation research to prove that this is sound, that it terminates, again, making sure that we have analysis that runs in finite amount of time, and then also we have provably improved precision over using some naive static analysis compared to just running the analysis on the framework and the application together. Okay, thank you very much.
Anybody got a question for Don?
Good. How?
Yeah, so if you're relying on using the framework as sort of an oracle to tell you things, how robust is this when they keep updating the framework? The little deltas over there to cause everything to collapse and you have to start over from scratch, or how does that work?
So the question was, how do we handle if the framework changes if we're relying on an oracle? Is that right?
Relying on it as an oracle.
Right. Well, we assume that the application uses a specific version of the framework, and if the framework is updated and the application is updated to run against that new version, we just run whatever version the application is using. We're not tied to a specific version of each framework. We use whatever version the application is using.
Okay, so more verification up next. Now we're going to hear about distributed systems from James. Other James. James W.
Yeah, so there will be a test at the end of this talk about which James gave which talk. So I want to share, since the purpose of this colloquium is kind of to teach the department about the Pulse Lab, I want to first share a very deep hobby of the Pulse Lab, which is sort of irresponsibly unlabeled graphs, okay? So this is a graph with two axes that have some labels on them, but there's no scale, it's kind of nonsense. But the point that I'm trying to make with this graph is that, kind of similar to the one that other James made, namely that it used to be really hard to build stuff, and I've spent a lot of time building hard stuff, and it's now getting easier to build verified applications. And so it definitely correlates with the time that I've spent in grad school. I can't guarantee that it's fully caused by my PhD, but at least maybe partially caused by it. So what makes the top left corner of this diagram so high up on the effort axis? I claim that the key challenge in verifying things like distributed systems is inductive invariance. And inductive invariance are required because these systems have infinite state spaces, as I'll explain in a minute. So through a lot of my work, I've tried different solutions to this problem. Early in grad school, I tried a fairly straightforward solution, which I like to call proof by grad student, which involved a lot of manual effort. And since then, I decided I don't really want to put myself through that every time I want to build a new distributed system. So I've been working on more automated techniques, both on the proof side and on inductive invariant inference. Okay, so that's kind of the high level, but maybe I should start by telling you what a distributed system is. This is a very accurate picture of a distributed system. Okay, so they look like this. If you see them in the wild, maybe don't approach. And what are they there for? Well, what they do is they power all the little icons on your phone. Okay, so behind each one of these apps is a distributed system that's managing databases and user data and so on in order to make the app work. These are also used for important actual infrastructure that may or may not be running on our phones, like planes, trains, and automobiles. And the problem with these distributed systems is that they're hard to get right. So to give you an example, one summer early in my PhD, I went on the internet and read the news, and I found 3 examples of distributed systems bugs. So the first one was that the New York Stock Exchange had to halt trading. The Wall Street Journal's website went down, and United grounded all flights, and these 3 distributed systems problems happened on the same day. So what's going on here? Well, these systems execute in unreliable environments where they're executing concurrently with other nodes, and they're exchanging messages that can be dropped and duplicated, and they're running on machines that can crash and reboot. And under all of these circumstances, the system is supposed to maintain its guarantees. Okay, and so in order to try to do that, you might think, well, let's test the system extensively. And as I'm about to argue, that's basically impossible because there are too many behaviors. And in fact, to make a bad pun, there are not just too many behaviors, but infinitely many bad behaviors. So it's really impossible to test all of the executions of the system. So I'd like to bring back Dijkstra here, and he tells us when exhaustive testing is impossible, our trust can only be based on proof. Okay, so what I've been doing in my PhD is applying proof techniques to reason about these infinite state systems. And what makes these particularly challenging is that these days we're actually able to apply proof to the implementation code itself, not to more abstract models. And that makes things both more exciting and also more challenging. Okay, so how do these proofs actually work? Well, we're going to start by modeling the system. And I'm now going to get into a little bit of math because I want to show you some of the cool ideas. So we model a system by constructing a mathematical model of its state. So we start with some, let's say, single initial state, which is how the system is initialized. And then we have a mathematical model for how the system makes progress a little bit, one step at a time. And we sort of unroll this step relation to get the state space of the system. And so each of these states is a reachable state that you can get to by starting from the initial state and then unrolling the step relation. And our goal is to prove that some property is true in all of these states. And again, there are potentially infinitely many of these states. Okay, so we want to show that all reachable states are okay. Let's try to write that in slightly more mathy terms. Here's a formula that says if state S is reachable in 0 or more steps from the initial state, then S satisfies this property okay. Okay, so this is the goal that we're trying to prove. And because there's sort of an unbounded number of steps on the left-hand side of this implication, direct approaches like enumerating states or testing-based approaches are very difficult to apply. So instead, what I'm going to do is apply maybe my favorite idea, full stop, which is induction. Okay, so the idea with induction is to find a property I such that 3 things are true. First, I is true in the initial state. Second, I implies this safety property okay. And third, and most importantly perhaps, is that I is inductive, by which I mean whenever I holds in a state S and S steps to S prime, then I also holds in S prime. Okay? And this looks perhaps relatively simple, but is actually quite deep. For example, you might notice that there's no hypothesis over here that S or S prime actually be reachable from the initial state. Right? All I know is that they satisfy this inductive invariant. Okay? And the way you should think about these inductive invariants is that they accurately summarize all reachable states in sort of a finite way. And in particular, they allow us to reduce this unbounded reasoning at the bottom of the under the line to a reasoning about only a single step above the line. Okay, this sounds great. The catch is that these inductive invariants are really hard to find because they, like I said, they have to accurately summarize all reachable states of the system. Okay, so one guess as a place to start on your search for an inductive invariant might be to say, can I make the inductive invariant the safety property itself? Okay, and if you try that, you'd be trying to prove this formula that says if the safety property is true and then I take a step, the safety property is still true. And that will typically not be something that you can prove because the specifications are typically not inductive. They don't talk about every aspect of the state in sufficiently precise detail to make this provable. So what you have to do is find a bunch of additional facts that you need to maintain in your inductive invariant such that this comes out to be the case. Okay, so I said that I summarizes all reachable states. What are all the reachable states of a distributed system, and what is this step relation that I've been talking about? So here's a fancy video to sort of show you what a distributed system is supposed to be doing. So these are all nodes in a distributed system. It doesn't really matter what the distributed system is. And what you just saw happen was a timeout fired, and then some node decided to send some messages, which are then being delivered. And the state over on the right-hand side is changing as these messages are being delivered and so on. Okay, and so as the system progresses, some nodes might fail, and then they'll stop responding to messages. And in order for the system to continue correctly, it's going to need to maintain its safety properties even in the presence of those failures. Okay, so we need to capture all of those kind of events, message delivery, timeout, failure, and so on, in this step relation. And that's sort of the basic idea of modeling these systems. So to give you an example of a system, together with my co-authors, we have analyzed something called the Raft Consensus Protocol, which is a distributed system that allows you to replicate a single node system onto multiple machines in such a way that you get high availability. And this is the part of my grad school experience that I was describing earlier that was a lot of work. So we did this in the Coq Proof Assistant. It was about 50,000 lines of proof. And like I said, it was kind of fun at the time, but I don't want to do it again. So when we did this, we actually were talking to the designer of the Raft algorithm who had tried to produce a proof himself during his PhD and decided that he could graduate without finishing the proof. But he was excited to hear that we had done it. So sort of the takeaway message from this slide is it was fun once, but not again. And so what makes this thing so hard? Well, really it's that we had to come up with the inductive invariant and then we had to prove it. So in the last minute or so of my talk, I want to tell you about some more automated solutions, both to proving inductive invariance and then even to finding inductive invariance automatically. Okay, so the first technique I'll tell you about is just some proof automation. So we had these 3 goals that we needed to prove about I. Suppose we had I and we just wanted to automate the proof. Then what we would do is try to express both the system model and I in a decidable fragment of logic, such as one that might be decidable by the Z3 SMT solver. So the logic that I like to use for this kind of thing is called effectively propositional reasoning, but other possibilities exist as well. And this is not always possible in theory because there exist undecidable formulas, and so you may not be able to express your invariant in any decidable fragment. But in practice, we have found that this surprising fact that it seems like there's always a trick to modeling your system in such a way that you can express it in these decidable fragments, which I find quite surprising. Okay, so that's a little bit about proof automation. What if we want to find I itself? Well, what we can do then is kind of similar to what other James was describing in program synthesis. We kind of want to synthesize this inductive invariant I. So you can think of this as a search problem over formulas that we want to plug in for I. And we have some work under submission right now that restricts the logic of I even further in order to make this possible. And sort of in parallel with the last slide, I would say this is not always possible in theory, but also in practice not always possible this time. So this is much more difficult, but even if it's only finding part of your inductive invariant, it can still save quite a lot of work. Okay, so just to summarize, we have unlabeled graphs, we have inductive invariance, we have proof by grad student, and we have proof automation and inductive invariant inference. And I'll be happy to take any questions.
Any questions for James about logic, inductive invariance, distributed systems verification?
So when you're writing these proofs about a specific implementation of a protocol, and you know you're stuck on something, how do you figure out whether the reason you're stuck is because there's actually something wrong with the implementation, or because you haven't quite got the right invariant yet?
That is a fantastic question. So it is often the case that the reason is because your inductive invariant is not right yet, but sometimes you do find bugs in the implementation. One thing that can help is if your proof technique can generate concrete counterexamples for you, which is definitely not the case in our Coq proof assistant work, but in some of the more automated techniques, we actually have counterexample generation working. And so when the proof doesn't go through, the system tells you, here's a concrete example state where if you take this step, you will violate something. And that can, if that violation is of the safety property, then that's a sort of constructive proof that your implementation is wrong.
Another thing that can help you figure out is if you could visualize the execution of the distributed system and sort of play with it. Which, Doug's up next, and maybe we'll learn something about that.
That was a great segue, Zach. Thank you. I'm Doug, and I'm going to be talking about a graphical interactive debugger for distributed systems. So first, I want to tell a little story, and please brace yourselves because it's a very sad story. James was talking about the formal verification of the Raft consensus protocol. The other person drinking the beer and eating the pizza and working on Raft was me. And since we did this verification, we've been sort of lurking on the Raft dev mailing list. And this is a sort of a typical email sent to Raft dev. So again, Raft is this distributed consensus protocol, and it's sort of complicated and tricky to reason about. And so a lot of people end up sending these emails about like proposed optimizations to Raft. So the details of this aren't important, but this is some kind of proposed optimization. And it's wrong because all of these proposed optimizations are universally wrong. Like modifying a distributed system in a way that actually maintains its correctness is for most programmers essentially impossible. And I sort of figured out why I was wrong and then replied to this person. And I think it was pretty polite and possibly a little condescending. But this is the email that I would have wanted to send, which reads, this won't work. These things never work. If you try to get it to work, you will end up deploying something to production that will lose your data and cause huge headaches for your users and your sysadmins. And this makes me really sad. I think that programmers should be able to experiment with the systems that they use and to be able to make modifications without sort of worrying that it's going to break and it's going to lose literally all of their data. So this is a huge bummer. So distributed systems, as James mentioned, are really important, like they're used in Snapchat. They're really difficult, and developers really need as much help as they can possibly get in order to implement them correctly. So most of my work is really focused on this. I've been working on sort of helping developers to build more reliable distributed systems. And previously, I've done a lot of work on formal verification. As James was talking about, I was part of the sort of proof by grad student strategy, mostly. But more recently, I've been working on other tools for helping developers, and especially very novice developers, such as students, to understand bugs in distributed systems. So understanding bugs, right? There are two main questions when you're trying to understand a bug. The first is, why is my system misbehaving? And the second is, what can I do in order to fix it? And the baseline that I'm sure most of us or all of us have encountered is just staring at the output of your program in a terminal, right? Staring at log files produced by like printf statements or whatever. A better solution to this problem would be graphical interactive debuggers, like those included in Visual Studio or Eclipse or IntelliJ. So what these graphical interactive debuggers let you do is to step through system execution, sort of line by line, examine the state of the system as it evolves, and you can also sort of run the program until some conditions are met and then examine its state once it's there. So this is a screenshot of Visual Studio, which is one of these IDEs that includes a debugger. There are a few features here, right, that correspond to those that I mentioned. So the program is currently paused here, and you can step through it by clicking buttons. You can look at the variables in scope here. So this shows you the current state of the system. And as you step through it, you can see how those variables change over time. And then this specifies like a breakpoint or a watch point. So a breakpoint means that if you just run the program, then the next time it gets to that line, it will pause. And then a watch point allows you to specify some conditions on the program state such that it will pause once it reaches a state matching those conditions. So can we use this kind of graphical debugger to debug a distributed system? So here's a distributed system on these slides. It's a very simple distributed system. It's just a client and a server. So what the client is doing is first setting this timer such that after 10 seconds, it will send the server a message that just says A. Then it's sending the server a message that says C, and then a message that says D, and then B. And then all the server is doing is just running a loop, receiving these messages, and then appending them to its state. So let's say that we're trying to debug this distributed system using a graphical debugger like Visual Studio, and we're trying to answer the question, is the server state ever ABC? Right? So we can say that like if the server state is ever ABC, this is a bug for whatever reason. Right? We don't want to get to that state. So the answer turns out to be yes. And how we would get to that state is first we would wait a while and then deliver this A message. Then we would delay this C message. Then we would drop the D message entirely, then deliver B, and then finally deliver C, right? So and this is because the network can sort of arbitrarily reorder the messages that you send. So my claim is that using a graphical interactive debugger like Visual Studio, there's really no way of getting to this state just by stepping through the program line by line. And so as a result, you're left with sort of the baseline case of just staring at log files, except now instead of just one log file, you've got as many as you have servers. So this is a sort of a bad situation. As James mentioned, the James immediately before me, distributed systems are difficult to develop because of the combination of concurrency and failure. And for exactly the same reasons, they're really not amenable to traditional debugging. And this is because in order to debug this program, the debugger really needs to be able to control the order of all of the events in the system, including messages and timers and failures. So I've been working on this system called Oddity, which is a graphical interactive debugger for distributed systems. And what it does is gives the users control over the ordering of these events. And currently it can be used on any system that's specified as a set of atomic event handlers. So Oddity sort of gives you the features of these graphical interactive debuggers on distributed systems. So it lets you step through the system's execution by controlling exactly which event happens next. It lets you examine the state of the system, so messages and timers, as well as the state of each node. And then I'm working on an implementation of watch points, which I'm hoping to be done for my PhD. So I'll now do an extremely risky live demo. And this is going to be Oddity running on a real distributed system. And it's actually going to match the distributed system from the example. So this is the same system that we saw earlier. So we have the client and the server. The client has scheduled this timer for it to send the A message, and then it sent B, D, and C to the server. So in order to end up with the state that we're trying to end up with, we can first deliver this A message, A timer rather. then deliver the A message, then deliver B, and then I'm going to make this very obvious mistake. So, okay, we're going to deliver D by accident. So this is bad, right? Now we're not in the state that we were going for. Luckily, Oddity implements time travel. So because there's so frequently so much non-determinism in distributed systems, you really want to look at multiple executions at a time. So we can look at the history of events down here, and then just click on the one before we made that mistake, right? So now D is waiting in the server's inbox again. We can instead deliver C, and then if we examine the server's state, we can see that it has state ABC. Okay, so in summary, Oddity lets you control the ordering that events happen in. It lets you inspect the node state, message contents, and timer contents, and also lets you navigate this branching event history, including time travel between various states. So we've evaluated Oddity by deploying it to a couple of classes here at UW, a professional master's distributed systems class, and then the most recent iteration of the undergraduate distributed systems class. We've integrated it into this new labs framework for distributed systems classes that Alice and I have been working on. The framework includes a model checker, and Oddity can be used for visualization of the counterexamples generated by the model checker. And students were encouraged but not explicitly required to use Oddity. So in general, students who did use it found it useful. Please talk to me about like giving research software to undergrads. It's really interesting and has some sort of unique challenges. Again, students are really enthusiastic about using it, but it can be difficult to actually get them to. But students were able to use it to diagnose liveness bugs, so cases where their system was failing to make progress, and then it turned out that it wasn't applying to clients, applying to clients at all, and this was really easy for them to see in the debugger. They were able to use it to diagnose performance bugs. So there's a case where the system was sending sort of totally unnecessary and redundant messages. This was totally invisible to the testing, but it was really obvious that it was happening in Oddity. They could just see that the messages were being delivered. And finally, they were able to use it to visualize the counterexamples generated by the model checker. And in particular, students found it useful to explore the alternative execution paths using the time travel feature. So in the future, both during my PhD and after that, I want to work on extending Oddity by integrating a model checker and making it applicable to more systems by interposing on the system calls that systems make. I'm interested in making other similar tools. So you can imagine like a graphical interactive debugger for operating systems. There are a lot of sort of naturally visualizable features in operating systems like the page table or the scheduler. And you could imagine a graphical debugger for those. And you could imagine other sort of education-focused graphical tools. I'd also like to continue the work that James and I were doing on formal verification. So you can get really strong guarantees for these particular classes of system. And I really envision a world in which we have better developer tools and better developers, so therefore all systems will be less buggy. Formal verification can ensure that a lot of classes of system actually have 0 bugs, and maybe eventually we can actually trust the software that's sort of powering our world. So thank you, and I'm happy to take any questions.
Any questions for Doug about deploying tools and visualizing distributed systems?
Yes, Doug, this really seems like a wonderful piece of, I guess, a wonderful tool for a developer to have at his disposal. My question to you is, in your opinion, do you think it's a little, I guess, weird, strange, or unexpected that people put up with the console whine form of debugging for so long, or what seems to be a long time?
I mean, I think it's really a result, I'm sort of speculating here, but it's what we're used to and it's what we're taught, right? So like if that's what we use in classes, right, we're mostly using printf debugging on like short programs. And so therefore we just sort of get used to it and we tolerate it. But yeah, no, I mean, it's terrible. Like it is bizarre that like this is sort of continues to be more or less the state of the art in many, if not most domains. Yeah.
Okay, sorry, we're gonna do, keep moving. Okay, so next Pavel's gonna talk to us about verifying visual layout of web pages.
All right, great. So as you might have noticed through these previous talks, there's sort of been a theme going on, which is taking these classic programming languages and software engineering ideas, like verification, language semantics, static analysis, and trying to extend them to new domains, whether that's frameworks for Java applications, distributed systems, file systems, and so on. And my work is also in this vein. You see, I've been working for these last few years on taking these classic programming languages and software engineering concepts and extending them to web page layout. Now, okay, web pages are like programs in a variety of ways, and I mostly mean not those. So web pages contain a back-end service that's usually written in something like Python or PHP, and also some front-end code written in something like JavaScript. And these are basically general-purpose programming languages. So applying the standard PL tools like verification and semantics to them is at least comparatively straightforward. But there's a third underappreciated component of web pages, as you can tell from the fact that the right-hand third of the screen is empty, which is maybe less obviously a program, and that's web page layout. And that's what this talk is going to be about. Now, I'd like to get into the details of how we apply PL concepts to web page layout, but first I want to convince you that web page layouts are programs. And I do have a demo video of this, but I think it would actually be better if I showed it to you live. So this is healthcare.gov. This is a website used by many people to get health insurance. And you can know that it's a program because the output of this layout, the image you see here, depends on the inputs to that rendering process. And those inputs aren't command line flags or files on your file system. They're things like the width of your browser window. So you can see that as I change that, the layout of the page changes as well. And eventually, if I make the page width small enough, it'll switch over to an entirely different website. So that's one of the inputs that we can pass to a website. There are others. For example, I can increase the default font size on the computer. And you can see that as I increase the font size, not only does the layout change, but it also reveals bugs, like this search box that's now floating outside the toolbar that it was supposed to be positioned in. If web page layouts are programs, and they can contain bugs, we want to apply verification and static analysis to them. So if we're thinking of web pages as programs, the first step is thinking about what specifications, what properties do we want to prove about those web pages. And for web pages, these are visual properties, things like no text overlapping other text, all of the buttons being on screen, or the headings forming some sort of consistent hierarchy. And we want to know that these properties hold because we're good web developers, because we want to make good web pages. But there's also legal reasons, like satisfying the requirements of the Americans with Disabilities Act. So there's a lot of reason to verify that these properties hold of our web pages. But it's not quite clear, how do you apply traditional PL concepts to this new domain? And that's really what my work has been about. Roughly speaking, there's been two big challenges we've had to surmount in talking about web pages as programs. The first is that we needed a way to describe how web pages behave, what a browser does. And the second is that we've had to have a way of describing what web pages should do, the visual properties that they ought to satisfy. So I'm going to walk through both of these really quick to give you some sense of what this work has contained. And the first is formalizing how web pages behave. Now, the behavior of web browsers is described by this extremely long English language document put out by the World Wide Web Consortium. And like any other extremely long English language document, it is both ambiguous and incomplete. Now, in contrast to this English language text, there's also the source code of actual extant web browsers. It's also very long, millions of lines of C++. And while it's complete in the sense that it tells you exactly what the browser will do, there are also disagreements between browsers and between browser versions. So to get some coherent understanding of how web pages behave, we had to combine the benefits of these two approaches. We did that by taking from this World Wide Web Consortium not the text of the standard, but actually a collection of conformance tests that browsers use to ensure that they're implementing the standard correctly. For these conformance tests, we can find the desired behavior, the thing browsers actually need to do, by running existing web browsers. And this combination of conformance tests and desired behavior covers the standard and allows us to ensure that every edge case is handled correctly. And by doing that, we've been able to describe the behavior of fairly complex web pages in ways that are consistent with existing web browsers, while also shrinking these pages and pages of text to a fairly short and clear 1,000 lines of code. So that tells us how web pages behave. But we'd like to know whether they behave the way they should behave. To do that, we need a way of describing the visual properties of web pages. So I'm going to just do this directly by example. Here's how, in our system, you describe that all the links on the page are on screen. In this logical formula, I've given a property that describes all boxes, all boxes on the screen. And that's that for all B in box. And a box is just some rectangular part of the page, text, or perhaps an HTML element. I've then asserted that if that box is a button, then it is on screen. In other words, that all the buttons in the page are on screen. And you can see that this assertion contains sort of three different kinds of statements. First, I have a property that describes a bit that talks about all of the HTML elements, all the boxes on the screen. Then I say something about the HTML that defines that element, like here that it's a button. And finally, I give some geometric property that that element has to satisfy, like here that it's on screen. So we've built a language that can do basically these three things. And it's expressive enough to describe a variety of accessibility guidelines, including things like from the Department of Justice implementation guide on the ADA. At the same time, we've made it possible to automatically check these assertions of a website for all possible combinations of widths, heights, font sizes, and even some of the weird parameters, like the width of your OS scroll bars. So that's been sort of our technical approach, and now I just want to give you a brief flavor of how we've evaluated and tested this tool. Now, the first thing I told you about was capturing the behavior of web browsers on real web pages. And so here I have a collection, a table of the unit tests that we've run. These conformance tests that we've gotten from the World Wide Web Consortium. And you can see that we've actually evaluated something like 3,500 of these tests across 45 different sections of the standard. And across those unit tests, we found that consistently our formalization either matches the browser or matches a bug in that browser's bug tracker. And these cover things like rounding errors or an incorrect implementation of floating layout. And now this tells us that our formalization is correct. But to make sure that our formalization is useful for determining the properties of web pages, we've gone further and collected 62 different web pages from common web templates and ran them against 8 accessibility properties that we've collected from things like the Department of Justice or the Apple Human Interface Guidelines. And so you can see here that of these accessibility guidelines, we generally verify web pages, and when we don't, we produce relatively few false positives. So here, we found 65 bugs across these 62 web pages and only 13 false positives. So that's been our approach to verifying web pages and ensuring that accessibility properties and potentially other visual properties like mobile friendliness or usability are valid across all possible inputs like width and height and font size to a web page. Thank you.
Any questions for Pavel about verifying web page layout?
Do you think it is possible also to formalize the interactive properties?
Right, so the question is whether it would be possible to formalize the interactive properties of web pages. And I assume you're talking here about JavaScript and the way JavaScript modifies web pages. There is. So we've been working in the last few months on trying to extend our tool to talk not about particular components of the HTML, but actually about components with generic content. So we might call this client-server reasoning, and what we'd like to do is to go from just layout to both the interactive component in JavaScript and also this server-side component. To do that, we'd like to, instead of talking about particular bits of HTML, talk about HTML that contains some unknown parameter, like the icon to show or the title of the page. And also potentially some side conditions that need to hold for those visual properties to be true. Like, for example, if the label is too long, perhaps that visual property won't work because the text will wrap outside the button. And so we've got some work in progress to apply this approach and try to verify both the web page visual layout, both before and after some JavaScript runs.
All right, folks, if you have any more questions, please find one of the speakers, afterward. But thanks, everyone, so much for coming to this kickoff colloquium. Make sure to be here, 3:30 next Thursday. We'll be hearing some talks from the theory group. All right, see you all. Let's thank all the speakers one last time.